Our very, very last lesson for this semester. Everybody's very excited. Yay. So the title is Orthogonality. The idea is the following. We defined what are inner product spaces. We defined the notion of an inner product. And we saw how via inner products we can get geometry. And I'm going to mention a brief reminder in a second. Once we have that geometry, we have notions of angles, and we have notions of length and distance. So that geometry provides further structure. But on the other hand, we kind of forgot all the purely algebraic stuff that we did before, right? There's a basis for a vector space. There are matrix representations for linear transformations. We discussed many things. And what I want to do very briefly, because this is really a topic that we're just touching, just introducing, kind of relate the two. Show, for example, how we make precise the notion of a basis like the standard bases in R2 and R3, where all the vectors are perpendicular, right? If you think of the standard basis for R3, the x, y, and z axes, and unit vectors in those directions, they're all perpendicular. There's 90 degrees between each two, right? So we want to somehow be able to say that for a general basis, and to see why is that good. Who cares? Okay? So those are the ideas that I want to discuss now. So, and in particular, what is this word, orthogonal? So here's a brief reminder, very brief. Via the inner product, which we denoted by u comma v on a vector space, we defined length, or the norm, or length, which was defined, the length of a vector was the root of the inner product of the vector with itself. We defined angles. So the angle alpha between two vectors was defined. Its cosine is the inner product of the two vectors divided by the product of their norms. Remember this? And we defined distances, or a metric. Which was defined, we used the notation duv. I don't know why I'm keep changing the order. Doesn't matter, of course. The distance between u and v is the norm of the difference. Okay, so this is the stuff that we did. And this is the geometric structure on an inner product vector space V. Okay. Now let's mention what we said about R3. Note that the standard basis of R3, let's denote it by E, and its elements are the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And let's call them E1, E2, and E3. Right? This is the standard basis in R3. Satisfies two things. One, the norm of EI. So what is the norm of EI? It's the product, the inner product of EI with itself, square root. But if you take each of these, what is the inner product? Let's put a reminder here. In R3, what is the standard inner product? In R3, let's let's even write it directly for the norm, because we said it already. The norm of v in R3 is the root of v1 squared plus v2 squared plus v3 squared, right? Everybody remember this? So what is the norm of each of these EIs? It's just 1, right? So the norm of each of these EIs is 1, and this is true for I equals 1, 2, and 3, for all three of them. Do you agree? And the second thing that these elements satisfy is that the inner product of EI and EJ, if you take the inner product of EI and EJ, and let's remind now what the inner product is. I should have switched the order of these, doesn't matter. So the inner product of UV in general is U1 V1 plus U2 V2 plus U3 V3, right? That's the inner product on R3. So if you take EI and EJ, two of these, you just have to sum the products of their coordinates. So what's going to be the inner product?
0.
0. Do you agree? If you, for I, not the same as J. Do you agree? Right? If you take, let's say, E2 and E3, their inner product is 0 times 0 plus 1 times 0 plus 0 times 1. Good, everybody? So this means that each of these vectors has length 1, often called a unit vector. Each of these standard basis elements are unit vectors. This means that they're pairwise perpendicular. Why? Why? So let's look back a minute at the definition of the angle. The angle was defined over here on this board. The angle was defined as take the inner product divided by the product of the norms and then do arc cosine. That's cosine of the angle. If this inner product is 0, then this is 0. So which alpha satisfies that its cosine is 0?
Pi over 2.
Pi over 2. Do you agree? So saying that the inner product is 0 means that two vectors have a pi over 2 angle between them, meaning they're perpendicular. Okay, so let's go back here and say this, say it in blue. So this means that EI has length 1. Length 1. And this means that any two are perpendicular. Okay, good? Okay, so let's make this a bit more formal. Here's the definition. U and V, in general, are called perpendicular, or, this is the professional algebraic word, orthogonal. Orthogonal. And denoted U is orthogonal to V. That's the notation, which makes sense, right? If their inner product is 0. This compiles, this makes sense in an inner product space where you have angles. Good? Okay. Let's maybe mention, since if UV equals 0, then cosine of alpha equals 0. Hence, alpha equals pi over 2. Good? Okay. So, in summary, the basis elements of E, the standard basis of R3, are orthogonal, pairwise orthogonal. Any two are orthogonal, and of length 1. Do you agree? Okay. Okay. So I want to take this notion of orthogonality in length 1 and define it for a general group of elements in a general vector space. So here's the next definition. A set, let's call it B, equals V1, V2, V3, Vn in an inner product space V. In an inner product space V is called orthogonal. So now I'm defining what orthogonal means for a set. Okay? If the inner product of Vi and Vj is 0, not always whenever I is different than j. Okay? For all I different than j. That's an orthogonal set. Okay? If in addition, the norm of each Vi is 1 for every I, then there's another name for it. Then B is called, it starts with ortho, but having vectors of length 1 means they're normalized. That's the word that we usually use. They're normalized vectors. And B is called orthonormal. That's the terminology. Okay? Furthermore, here I just said this is a set. But if it's more than just a set, if it's a basis, and I was hinting to that by calling it B, if B is a basis for V, linearly independent and spans the entire space, then it is called an orthogonal basis or orthonormal basis. Orthonormal. 1 second. Basis. Question? Yes.
If Vi is different from Vj and it's all the Vi, Vj's are 0.
All the inner products.
Inner products are 0. It has to be linear independent. No?
So there are theorems in this direction. Okay, there are theorems in this direction. Well, it doesn't have to span. If you take two vectors, okay? So there are theorems in this. It's a very good observation. Okay, does orthogonality imply being a basis? Not quite, but it does imply. Okay, good. But I'm not going to go into those details. Okay, as I said, we're just touching. Just touching. There's a whole theory that can develop from here, and in fact, this theory extends beyond finite dimensional spaces even, okay, where things become a lot more interesting, okay, at least to me. But we're really just touching. We're really just putting some definitions. I'm going to prove exactly one tiny little very useful fact, but that's it, okay? Semester ends. Come again next semester. Well, not to this course, to the following courses. Okay, but very good observation. Okay, so is it clear what an orthonormal basis is? So now that E, the standard basis of R3, is an orthonormal basis. Okay?
Are all the standard bases that we've used so far like orthonormal? Is that how you define the standard basis?
Well, you can define the standard basis as being an orthonormal basis because there are many, many more than just the standard one. But the standard bases we had were orthonormal. Yes, yes. In fact, they were all the same basis in disguise, right? They were all those, that E, well, not necessarily for R3, but for Rn, where we just, if we thought of polynomials, then we took the standard basis, but in terms of the coefficient vectors, they were the same thing. And we know that these, once two vector spaces have the same dimension, they're the same vector space. Not quite, they're isomorphic. There are two ways of looking at the same vector space, and therefore their bases are just translations, right? So answer yes. Every one of those what we call standard bases, like for polynomials 1, x squared, x cubed, and so on, is an orthonormal basis, but not vice versa. You can have many orthonormal bases which are not the standard bases. Okay? Okay. You really wish there were at least 3 more weeks to this semester, right? And we can go on. We're having fun. Okay, good, good. I like that. Okay, so example E is an E from the previous example is an orthonormal basis of R3. And if you want, that's a very good exercise. Take, for example, in 2 by 2 matrices, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and I skipped one because I only said 3 and got to the end. But take the 4 standard basis elements in 2 by 2 matrices, show that they're orthonormal. Orthonormal with respect to what? Orthonormal means a statement about the norm and a statement about the inner product. So you have to say what is the inner product on matrices and what is the norm that it gives rise to. Take the standard inner product and the standard norm. Okay, good? So those are good exercises. Okay, so once we have this notion, it's very, very straightforward. So suppose somebody throws at us a bunch of vectors, just a set. Maybe that set is a basis. Maybe it's just a set. Suppose we want to form from it an orthonormal set. Okay. So what do I mean form from it an orthonormal set? I can always take all the elements, throw them away, take different ones, and said, hey, I formed from it an orthonormal set. But that's not interesting. So what I mean is, suppose you have a set of vectors, and that set of vectors has a certain span. It spans some subspace, maybe the entire space. Suppose you want to form from them a different set with the same span, that is orthonormal. Okay? So there are 2 things you have to do. The first thing is you have to normalize them. You have to take each one and make sure it's of norm 1. Okay? And that's easy. That's easy. So here are some remarks. It is easy to normalize a vector. So suppose somebody gives you a vector v, and you want a vector with the same span. What is the same span as a single vector? It just has to be some multiple of that vector, right? That's the span of a single vector, all scalar multiples. So the way to do it, so suppose it is easy to normalize a vector v. Take 1 over the norm of v times v. Okay? The norm of v is a number. Well, to normalize, have to be a bit precise here, a non-zero vector, v. If v is the 0 vectors, there's nothing you can do to it to make it of norm 1. There's no scalar multiple of it of norm 1. But if it's not, then this is what you do. Okay? The norm of v is not 0. It's a number. 1 over it is a scalar. Take that scalar multiple of v. claim. It has the same span as V. I didn't change anything, right? It's just a scalar multiple of V. And it has norm 1, because what is the norm of alpha V? Since the norm of 1 over V times V, right? The norm of a scalar times a vector, the scalar can come out of the norm in absolute value, right? But this is already non-negative, a non-negative real number, so it's just 1 over V came out of the norm, and here I have norm V. And that's 1. Do you agree? Okay, so normalizing a vector is very easy. And if you have a bunch of them, you just normalize each one separately. But that doesn't guarantee the second property of being an orthonormal set, or the first property of being even an orthogonal set, that pairwise they're perpendicular. Okay? That their inner product, the inner product of each two is 0. And there's a way to do that. And that's a much more sophisticated algorithm. Okay? Because once you deal with two vectors, then you want to take care of a third one, you're messing up the first two. Okay? So I'm not going to describe it in detail. Okay? I'm just going to say a more sophisticated process called, named after two mathematicians. No, not Cauchy Schwarz. That is something else, as you know. Gramschmidt. Double M or single M? I think single M. Schmidt. Called Gramschmidt. So it's an algorithm. It's an algorithm whose input is a set of V1 to Vn vectors. Okay? They have to be linearly independent if you want to have the same number of vectors at the end. Okay? You throw them in, you get out a set with the same span, which are orthonormal.
You always can do that?
You always can do that in a finite dimensional space, yes. Okay? But many of the things I'm saying here can be extended to infinite dimensional spaces, but they're beyond the scope of our course. Okay? Okay, so a more sophisticated process called Gramschmidt enables to take any linearly independent set in particular a basis, of course, and produce an orthonormal set with the same span.
The norm stays the same.
One second, with the same span. Say that again?
After this process, the norm stays 1. If it was 1 before or no?
They normalize it.
Yeah, the process does two things. Okay, and I'm not saying in which order, and in fact, what it really does is first orthogonalizes them and then normalizes the result. It doesn't change the orthogonality. Okay, so it produces a new set. In general, none of the vectors are gonna stay the same. They're all gonna be modified. Okay, but the span will not change. Okay, so in every step, the span remains the same. Okay, and that requires defining a notion of projecting one vector on another, and then once you do that, you need to define the algorithm and then prove that it really does what you're claiming that it does. It's not hard. Probably even if you open the Wikipedia entry, you would see it with an example and everything. Okay, it's not difficult, But again, I'm not going to go into the details now. Okay? So given a basis, for example, you can always produce an orthonormal basis from that basis.
Isn't this kind of similar to basically the basis transformations that we did previously, like moving from one basis to the standard basis? That's kind of turning it into an orthonormal basis.
I'm not sure I understand your question, but let me say this. If you're looking at the entire space, then, and you're saying, hey, give me a linearly independent set, okay, I will produce an orthonormal set with the same span. I'll just take the standard basis, right? It becomes interesting when you're taking subspaces, okay, where you can't just say, I'll take the standard basis because it's a subspace. It has some restrictions. Not all the elements are there. And you still want to take a basis of the subspace and make it orthonormal. Okay, I don't know if that answered what you were asking, but otherwise you can do it very, very naively and in a very uninteresting way. Okay.
So we can definitely normalize a vector to turn it into an orthogonal one?
Yeah, normalizing a single vector is just this. Okay, you get a different vector. If you started with the vector 5, 0, 0, by normalizing it, you would get 1, 0, 0. It's a different vector, right? But now take 1, 0, 0 and take 5, 0, 0 and 1, 2, 0. 5, 0, 0 and 1, 2, 0, they span a two-dimensional subspace of R3. You can normalize each of them separately, but they're not perpendicular, right? Their inner product is not 0. Their inner product is 5. Okay? So how do you make two vectors that are perpendicular of norm 1 that span the same subspace of R3 spanned by 5, 0, 0 and 1, 2, 0? Okay? Okay. So good. So we know what an orthonormal basis is. We know there is a method, okay, accessible in the literature or the electronic literature, to produce orthonormal bases. And the next question is, what are they good for? Okay. So here are partial answers, preliminary answers to what orthonormal bases are good for. When you have a basis, the first thing you know about a basis, that's what a basis is all about, is that you can take any element in your space and write it as a linear combination of basis elements, right? The basis encodes everything about the space algebraically, everything in terms of what are the elements of that subspace, right? But what are the coefficients? Suppose I give you a vector, and I tell you, hey, this guy is in the linear subspace spanned by 5, 0, 0 and 1, 2, 0. How would you know how to write it precisely as alpha times 5, 0, 0 plus beta times 1, 2, 0? You would need to solve a certain system of equations, right, and produce those alphas and beta, alpha and beta, right? But if it's an orthonormal basis, they're right there looking at you, the coefficients, okay? So that's the following statement. If B equals V1, V2, V3, Vn is an orthonormal basis, of V, then this is a theorem. This is actually a theorem. I'm even going to prove it. The proof is very easy. Then, for every V in V, I know exactly how to write it as a linear combination of the VI's, as follows. V equals, it's going to be the sum of alpha i's VI's, right? Alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3, etc. So I'm going to write it in summation notation. Sum I equals 1 to n. Here are going to be the coefficients, alpha i's times v i's. Do you agree? Right? Every vector is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. But I'm going to tell you what these alpha i's are. The alpha i's are none other than the inner products of v and vi. So alpha 1 is the inner product of v and v1. Alpha 2 is the inner product of v, the vector you're trying to write as a linear combination, and v2, the second basis element. Alpha 3, the coefficient of v3, is the inner product of v with v3. The coefficients are precise. Okay? Let's prove this. Is it clear what the statement is? Everybody? Okay. So these are precisely, maybe let's emphasize these, the alpha i's in expressing v as a linear combination of the vi's are explicitly given by the vi's themselves if it's an orthonormal basis. Okay? Let's prove this. Let's see that this is in fact the case.
The end of the sigma depends on the dimension of the space we're working on?
Right? If it's a space of dimension n, a basis has n elements, and every element can be written as alpha 1 v1 plus dot 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 alpha n vn, right? Okay, so here's the proof. Here's the proof. So let's take a v. So v, a priori, I know that b is a basis, then v can be written as alpha 1 v1 plus alpha 2 v2 plus dot 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 alpha n vn. These alphas exist for every v. Do you agree? Okay, that's what it means to be a basis. And we even know that they're unique, right? A basis expresses every vector uniquely in terms of the coefficients, right? Okay. Now let's see what is the product of the inner product of v and vi. I'm going to do some calculations and see that this just equals alpha I. And that's the claim. That's precisely the statement of the theorem. Right? So let's show that v comma vi is nothing but alpha I. And what ingredients do we expect to go in here?
V and vi?
All the alpha I, vi.
No, I'm asking what are the whatever the steps are going to be, what are the justifications that we expect to see that enable this magic to happen?
The definition
The definition of what?
of the orthonormal.
The orthonormality. That's the point, right? We expect to somewhere use the fact that this is an orthonormal basis and not just any basis. Okay, good? Okay, so let's see that. So what is v comma vi? V comma vi is v comma, sorry, that is what I wanted to replace. Instead of v, I want to write what v is. Alpha 1 v1 plus alpha 2 v2 plus dot 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 alpha n vn, comma, and now I'm multiplying by vi. Do you agree? Good? Okay. Now, right, what we have here is an inner product of a linear combination with a vector, and we know how to we know the linearity of the inner product in the first term. So we can break this into a bunch of inner products, alpha 1 v1 times vi, plus alpha 2 v2 times vi, right? So these are properties of the inner product. So this equals alpha 1 v1 inner product vi plus alpha 2 v2 inner product vi plus dot 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 alpha n Vn, inner product Vi. I have to erase this blue stuff because it's getting in the way. Do you agree? Furthermore, we know how to pull scalars out of the first component. They just pull out, right? So we have alpha 1 V1 Vi plus alpha 2 V2 Vi plus dot 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 alpha n Vn Vi. Right? We still didn't use at all the orthonormality. Here it comes. The inner product of V1 and Vi, if I is not 1, it's 0, because I is different than J. If I is 1, the inner product is 1, because it's the norm of Vi squared, right? So let's write that. So this equals, so using the orthonormality, Vi, Vj, or let's, since Vi is fixed here, let's write it as Vj, Vi, Vj, Vi is 0 for for j different than I, right? That's the orthogonality of these Vi's. And furthermore, Vi, Vi is the norm of Vi squared, right? Because the norm of Vi is the root of Vi times Vi. So this is the norm of Vi squared, and this is 1. That's the normality part of the orthonormality. Okay, so this is the justification for this step, right? And what it says is that the only thing that's going to remain is alpha I times Vi, Vi, which is in turn alpha I times the norm of Vi squared, which is just alpha I. Clear? Everybody? Okay, so that's it. We proved it. If you want to write V as a linear combination of the VI's, the alpha i's are none other than the inner products of V with each of the VI's. Okay, and they're very easy to calculate. You don't need to solve systems of equations and whatnot. Clear? Moreover, if you want to know the norm of a vector, you can calculate it in terms of these coefficients. Let's write that as well. Only if you're working with an orthonormal basis. In general, this is not true. So in many statements that we had, in many things that we did, we started with let V be a vector space and let B be a basis. Okay? You can expect that in inner product spaces and things that follow, okay, you'll hear words and terms like Hilbert spaces and many things that expand from this. Many theorems will start with let V be an inner product space and let B be an orthonormal basis. You can always have one. That's the Gramschmidt statement. And furthermore, it's useful. Good? Okay. So here's the second claim. So let's call it a theorem again. If B equals V1, V2, Vn is an orthonormal basis, then for every V, the norm of V equals the root of the sum, I equals 1 to n, of the absolute values of the inner products V, Vi. squared root. In general, these can be complex numbers, right? So this is not the absolute value, but rather the modulus. Okay? So if you want to calculate the norm of a vector, that's straightforward too. Calculate these. These are just the coefficients of writing it as the sum of the VI's, and take the square of these coefficients and take the square root. Okay, again, explicit in terms of the basis elements. Okay, let's prove this. And again, the proof is going to amount to very simple manipulations with inner products, and something's wrong.
Yeah, just a quick question. Why do we need to take the absolute value before we square it? The absolute value of the inner product.
Because if it's a complex number, you don't need the length.
Yeah. Well yeah. Right. If it's complex. Okay. We'll see that what shows up here is in fact the number times its complex conjugate, which is the same as the modulus squared. Okay. Okay. So let's see the proof. So we know that the norm of V is just the root of the inner product of V times V. That's how we define the norm in an inner product space, right? So it's implicit here, I didn't write it, that if B is an orthonormal basis, orthonormal is in an inner product space, orthonormal with respect to that inner product, right? And this norm is with respect to that inner product. We're assuming that the structures are agreed, that we're taking structures that stem from the same given inner product. Okay, if you take a different inner product, orthonormality changes meaning, right? And if you take a norm that doesn't come from that inner product, things just change. Okay, so that's something to keep in mind. Okay, so if I want to calculate V dot V and show that it's this sum, and that would prove the theorem, right? Because then we'll just put it in the root. Okay. So what is V dot V? I'm saying dot because we know that it's the same thing, but our notation is this. So what is the inner product of V with itself? So remember that we know how to write V by the previous theorem, right? So I'm going to do it. So V inner product with V is the inner product of... This might be a bit confusing. I hope you can manage the confusion. So it's the sum of VVI, VI. Let's make this bigger. The inner product, this is V, right? That was the previous theorem, comma, and this is V again. Do you agree? Good? Now, this is a sum, and this is a sum. Okay? I can open them up and write this as V V1 V1 plus V V2 V2 plus V V3 V3 plus, and so, and likewise here. But let's try to do it without opening them up, just in here. And what do we get? So we're going to get coefficients, these are numbers, times the VI's, a linear combination, times another linear combination. We can use the linearity of the inner product, right? And we know that the linearity of the inner product is a bit tricky. In terms of addition, it works perfectly, right? So if we take the coefficient of V1, if we take something times V1, it's going to meet each of the VJs here, right? And vice versa. But in terms of pulling the scalars out, scalars from the first component pull out as is. Scalars from the second component pull out with a bar. Do you agree? So what we get here, and you have to think a minute and tell me if you agree. And I'm using again the orthonormality. Orthonormality. phi. That's what I'm using here. So whenever we get one of these vi's to meet a vj, which is not vi, that component is 0. Okay? So the only thing that remains is for each of these, when v1 meets v1, when v2 meets v2, when v3 meets v3, etc. Okay? So the only surviving things are sum I equals 1 to n when vi meets vi. Do you agree? Good. And what are the coefficients? The coefficient of vi, let's move this even a bit more because I need a bit more space. So there are going to be coefficients times vi, vi. When I is different than j, it's going to be 0. Okay? And what are these coefficients? The coefficient of vi on the left term was vi. So that's the coefficient of vi on the left term. That's its alpha, came out of the inner product. The coefficient of the vi on the right term was vvi as well, but when it comes out of the inner product, it gets a bar. So I have here vvi bar. Do you agree? Now this is just a 1. This is the norm of vi. This is just a 1. And the inner product of a number times its complex conjugate is the modulus of that number squared. So we get sum I equals 1 to n modulus of vi squared. And therefore, the norm is the root of that thing, and that's the theorem.
Just can't understand why you left the sums.
Here?
Yes,
because there are n of these. When v1 meets v1, I get this one. When v2 meets v2, a priori, there are n squared additive components here. N squared, because each vi meets each vj. Okay? But most of them are 0 because of the orthonormality, because of the orthogonality. Right? And only n of them survive. And those that survive, this is just a 1. Right? Good? Okay. So this addresses, at least in part, at least in a very motivational level, the usefulness of having an orthonormal basis. We know how to write elements, how to write norms very, very explicitly. Okay? And in applications, these v's can be matrices, these v's can be functions, these v's can be many things, and we know how to write it. Okay? And when these v's are functions, for example, when these v's are functions, for example, what were these coefficients? Do you remember? What was the inner product on function spaces? I mentioned that. Was the integral. Remember? We had an example. Take f and g, and the inner product is going to be the integral of f times g, or f times the complex conjugate of g, if those are complex valued functions. Okay? So things really become very rich and very interesting, and with vast amount of applications. Okay? One more statement, one really final statement. Suppose that we have a linear map. We know that we can sometimes, not always, diagonalize it. Diagonalization is a process which, in particular, involves a basis, right? And we're kind of picking out that basis as the basis we want to work with, since it produces a diagonal matrix. A matrix with a bunch of zeros and easy to work with, right? That was the whole idea of diagonalization. Wouldn't it be nice if we could not just diagonalize with any basis, but diagonalize with an orthonormal basis? Okay? And that is called, wild guess, Orthonormal diagonalization. Say that 5 times quickly in a row. Orthonormal diagonalization. Okay? That's precisely the statement. It can't always be done, but sometimes it can. Okay? So that's the next statement, and in fact, the last one. So once again, we're only tapping on a broader discussion. Let's write it as a theorem. I'm not going to prove it, though. I'm not going to prove it. Let A n by n be a symmetric matrix over R, let's say. Remember what a symmetric matrix is?
All the
A equals A transpose.
Exactly. A equals its transpose, right? That's a symmetric matrix. Okay. So the claim is then A admits orthonormal, and but there's a terminology thingy here. So A admits orthogonal, that's what it's called, orthogonal diagonalization. Okay, so what does it mean, admits orthogonal diagonalization? It means, i.e., A has a diagonal form, D, and saying that A has a diagonal form, there is an invertible P such that D equals P inverse AP, right? They're similar via that P. The P is going to have the eigenvectors as columns, remember? Okay, so, but P is going to be, so i.e. D equals P inverse AP, where D is diagonal, and it's not a different D. D has the eigenvalues along its main diagonal. And P is what's called an orthogonal matrix. Bless you. And an orthogonal matrix is a matrix meaning that the columns of P, which are what? What are the columns of P? Right, the eigenvectors. So let's write is an orthogonal matrix, which by definition means that the columns of P, which are the eigenvectors in this case, which are the eigenvectors of A, are not just orthogonal, but are orthonormal. That's the terminology. The terminology is a bit misleading in this case. So the columns of P are orthonormal. And in this case, an orthonormal basis, right? Because if it's diagonalizable, then we have an orthonormal basis for... Okay, so note the bit of trickiness in the terminology. That's what it's called. It's called orthogonal diagonalization, and it means that P is an orthogonal matrix, but an orthogonal matrix means that its columns are orthonormal and not just orthogonal. Okay? Okay. And by the way, remark, the definition of an orthogonal matrix is usually not this. This is equivalent to the definition. But the standard definition that you would see is that P inverse and P transpose, which a priori are completely different notions, right? The transpose is just a transpose. The inverse is a more subtle process, right? But a matrix is an orthogonal matrix if and only if they coincide. Okay, P inverse and P transpose are actually the same thing. Okay, so those are nice matrices. They're easy to find the inverse of, right? Okay, I'm not going to prove this, but in fact, it's even an if and only if statement. So A admits an orthogonal diagonalization if and only if it's symmetric. Okay, it's not that you can have other matrices that admit orthogonal diagonalization, and you can see the relation to being symmetric. But okay, so I think we're going to stop here. Okay, this is just really giving you a flavor of where things, in which directions things can proceed, and in many other directions. But we're going to stop here. This ties up the notions of an inner product, which is hidden in this word, right? An inner product in the geometric structure with the topics that we've discussed previously in this course, okay? And yeah, questions on all of this? Everybody happy? Was fun? Okay, so you still have a lot of work to do to practice these things. You're going to see them in exercises and in tutorials and so on. And I wish you all a lot of success in whatever direction you take. And thank you.